Hello students, let's start with the chapter Magnetic Effect of Electric Current. In the previous chapter, you have studied about heating effect of electric current. You all know that whenever electric current flows through any conductor or flows through any circuit, part of electrical energy is used to do some useful work and rest gets converted into heat energy. If the circuit is purely resistive, it means if the circuit consists of combination of resistors or a single resistor only, then the entire electrical energy gets converted into heat energy. And you are also familiar now with the law, Joule's law of heating, which gives the measurement of heat produced in a conductor having resistance R when electric current I is flowing through it for certain time t. So in this chapter, we are going to see one of the other effects of electric current, that is magnetic effect. Before we start with this magnetic effect of electric current, let us recall certain terms. We will see those terms, we will recall those terms, but we will not go in depth. Okay? So let's first see what is magnetism. Now, in simple words, we can say magnetism is the property of attracting iron. So the property of attracting iron is called as magnetism in simple words, and we can say materials or things which possess this property of attracting iron are called as magnets. Now we are not going to go in depth, but we should know that there are natural magnets as well as artificial magnets. Natural magnets which are available in nature and artificial magnets are man-made magnets. All of you must have heard about bar magnet. You must have seen bar magnet in your lower classes. Now bar magnet is a linear magnet and it has two ends. You know now that magnet is something that attracts iron. So when we talk about bar magnet, hope you know the properties of bar magnet or properties of magnets. We know that when we hang a bar magnet freely, when it is freely suspended from a rigid support, then it is going to point only in one direction. When it is allowed to, when it is rotated, then also it will come to rest only in one particular direction, north-south direction. So its one end always faces towards North Pole and the other end always points towards South Pole of the Earth. The end of the bar magnet which points towards North Pole is called as North Pole of the magnet, while the other end which points towards South Pole of the Earth is called as South Pole of the magnet. So now we know that when we talk about magnets, we'll be considering generally bar magnets now. So bar magnets, they have two poles, North Pole, South Pole. And we know that when we bring, suppose a magnet is freely suspended. Now I am not drawing the diagram here as you people have done this in lower classes. So let's just recall. So whenever a bar magnet is suspended freely, or let me draw the diagram otherwise. So let's assume that a bar magnet is suspended freely from a rigid support here. Now this north pole of the magnet is lying towards this side. Obviously when it is freely suspended and this magnet is not close here, it means this side we have north pole of the earth and this side we have south pole of the earth. So the end which is pointing towards north pole is called as north pole of the magnet, and the other end which is pointing towards the south pole of the earth is called as south pole of the magnet. Now if I bring another magnet close to it such that the north pole of the other magnet is brought closer to the north pole of this magnet, then this will show repulsion. So this north pole will be repelled when we bring this magnet here, and when we bring the south pole here, then it will be attracted. So from this activity we know that like poles repel each other and unlike poles attract each other. It means north pole will repel north pole, south pole will repel south pole, and north and south will attract each other. So now we know the two properties of magnets. For one, that when freely suspended it always points in north-south direction. Secondly, that like poles repel each other and unlike poles attract each other. Now, let us see what is magnetic field. Now, if you have a magnet, then if you bring another magnet close to it, then obviously you can see the effect of one magnet on the other. Okay, I'll explain it to you here. Just wait. Now, this magnet, when it is brought closer, this magnet is showing repulsion because north is facing north pole of this magnet. Had it been there no magnet, then obviously this would not have moved. So this is moving only because of the presence of this magnet close to it. They are not in contact. It means we can say space around this magnet in which its magnetic influence can be felt. Now the magnetic influence will be felt by iron or it will be felt by other magnets. Okay, so in this case, the space around the magnet in which its magnetic influence can be felt by other magnets, we can say, is called as its magnetic field. Every magnet has its magnetic field. It means if this magnet has its magnetic field and you bring iron close to it or you bring another magnet close to it, it is going to be attracted or repelled depending upon which end is facing, which pole of one magnet is facing the other pole. Okay, so now here, so what is magnetic field? The space around the magnet in which its magnetic influence can be felt by other magnets or by other magnetic materials. It means magnetic influence means magnetic force. Now magnetic force can be of attraction or repulsion when we are talking about two magnets. Okay, but when we have iron placed close to this, it will be attracted by both the poles. When we take any other magnet, then depending upon whether like poles are close or unlike poles are close, there will be force of attraction or force of repulsion overall. So till now what we have done is, what is magnetism? What are magnets? What are the properties of magnets? Like we have seen that when freely suspended, a magnet always points in north-south direction and like poles repel each other, unlike poles attract each other. Then we have seen what is magnetic field, space around the magnet in which its magnetic influence or force can be felt. Now, let us see what are magnetic field lines. Now, to understand magnetic field lines, let us have a look at this diagram. Now here assume that you have a drawing board. Drawing board is a wooden board whose dimensions are, it is rectangular in shape with the dimensions approximately we can say 1.5 by 1 feet, 1 feet by 1.5 feet. It is made up of soft wood so that you can easily, that board which we use for finding the refraction of, to do the activity of refraction of white light through a glass slab, we use a drawing board, wooden board there. Same board can be used here. So on the board, we fix a white sheet of paper and then we can fix it either using adhesive or by using thumb pins. We can place a bar magnet at its center and sprinkle some iron fillings on the page. Uniformly we have to sprinkle the iron fillings, okay? And if we tap the board gently, what we will see that the iron fillings will arrange themselves in this pattern. See, I have shown here by dotted lines. Iron fillings, they are obviously made up of iron and they are very light. So just using a sprinkler, you can sprinkle them or you can, just spread them uniformly on the white sheet. And when you tap the board, the fillings will arrange in this pattern. It means the iron fillings, they are experiencing the magnetic influence of this magnet. So they are lying in the magnetic field of this bar magnet. They have aligned themselves in this direction. See, as shown in this pattern, they have aligned themselves. And we can easily see that near the ends, this is a rough diagram here, near the ends means near the poles, North Pole and South Pole, we can see more dotted lines there. It means more iron fillings are actually concentrated now near the ends of the bar magnet. So they are experiencing more force there, or in other words, we can say magnetic field is stronger near the poles of the bar magnet. Now this is the just, to have an idea, we have discussed this activity. Otherwise, there is one more activity using which you can actually draw the magnetic field lines around a bar magnet. Now, what are magnetic field lines? These are the imaginary lines which we draw on a paper to represent the magnetic field. Now, in case of bar magnet here, we have seen that iron fillings align them in this pattern. So we can see here that iron fillings align themselves in this way, along these lines, right? So these lines along which iron fillings align themselves are called as magnetic field lines for this bar magnet. Now let's discuss an activity using which or through which you can draw the magnetic field lines around a bar magnet. Again, you take a drawing board, fix a white sheet on it, and then place the bar magnet at its center. You can draw the boundary of the bar magnet using a pencil. After placing this bar magnet here, this represents a magnetic compass. You know what is magnetic compass? Magnetic compass has a magnetic needle in it which is freely pivoted at its center. And it is like we have a freely suspended bar magnet. Here, this is a tiny bar magnet which is pivoted at its center. And you know that even when we rotate this magnetic compass, suppose this bar magnet is not there, then even if we rotate it, this needle is going to point in one particular direction only. And this arrowhead indicates the north pole of the bar magnet or magnetic needle, and this side is the south pole. It means when no other magnet is close, so whenever magnetic compass is placed, this needle will point always in north-south direction. So here it is a tiny bar magnet. So here I have this bar magnet, and this magnetic compass, I'll place it here. We know that north will repel north pole. So this arrowhead is the north pole of the bar magnet, this tiny bar magnet, magnetic compass needle. So it will be repelled by this, and let us say this is the direction of the needle. So what you do is, so here once you have placed this magnetic compass close to this is the position of the needle. So you just mark these 2 points. Mark the 2 points means here mark the position of the north pole and this position of the south pole. Similarly, we can place then after marking this, we can place a magnetic compass here somewhere close to this place, and then again we can note down the position of the needle, and then we can mark north pole and south pole's position. So we can repeat this process. For each position of magnetic compass, we can have 2 marks. So I have shown here that first, second, now I have placed a compass here, then here, then here. So this way we can place a compass at different positions around the bar magnet, get 2 marks for each position, and then later on we can join those marks and get this line. Similarly, when you place the magnetic compass at different positions here, you can draw one more line and then one more line. So you can draw 3 to 4 lines above the bar magnet and 3 to 4 lines below it. So these lines are nothing but the magnetic field lines. So let me draw the magnetic field lines for a bar magnet now. So if the question is discuss an activity using which you can draw the magnetic field lines around the bar magnet, you can explain the activity which I have explained you just now. Or if the question is draw the magnetic field lines around a bar magnet, then you can just draw it. If the activity is not asked, you can simply draw it like this. Draw the bar magnet, draw this rectangular shape. Okay. And then draw a horizontal line from the center. Just wait, I'll draw it first otherwise and then explain you. So using the previous activity, we can draw the magnetic field lines. Now, if you are asked to draw the magnetic field lines directly for a bar magnet or magnetic field for a bar magnet, you will draw it in this manner. Now, see what I have done. I have taken one horizontal line at the center of a bar magnet. That is, see this straight wire, this straight line. It should be extended actually on both the sides. We can extend it. Then I have drawn here 6 lines below this, 6 lines above this central line inside the bar magnet. So for simplicity, you can just draw 4 lines above it and 4 lines below it. So all these 7 lines or all the 13 lines in this case, they are equidistant and they are parallel lines inside the bar magnet. Now below we can see this is the first magnetic field line, this is the second magnetic field line, this is the third magnetic field line, and so on. So this is how you're going to draw the magnetic field lines around the bar magnet. Now when I have discussed the previous activity, we were knowing that this side of the bar magnet is North Pole and this side is South Pole. So we are supposed to write here North on one side and South on the other side. It is your choice. You can write North, South or South, North. Now, if I consider this to be North Pole, when I place a magnetic compass on this side, right, we know that North Pole will be repelled. So here, if there is North Pole at this end, then North Pole would repel from here. It means it will point in this direction. So actually magnetic field lines represent the magnetic field, and magnetic field is a vector quantity. It has magnitude as well as direction. So in this case, you must not have understood actually what is magnetic field line properly. Till now you know that the lines along which iron fillings arrange themselves when placed around the bar magnet, when the sheet is or board is tapped gently, they represent magnetic field lines. But what is the exact definition of magnetic field lines? You are not knowing that. We can, in simple words, we can write magnetic field lines are the imaginary lines drawn around the magnet in which the magnetic influence is felt by the other magnets. It means magnetic field lines are the lines which represent the magnetic field. Now in this case, since magnetic field is a vector quantity, so here we must say that magnetic field lines should represent vector quantity, means it has magnitude as well as direction. So magnetic field lines should give us an idea of the strength of magnetic field and as well as direction. Now, in the previous activity, we have seen that near the ends of these magnets, iron fillings concentration is more. They get accumulated more near the ends of these bar magnet. So here it means strength of magnetic field is more near the ends, more near the North Pole and the South Pole. We can see here that the magnetic field lines are crowded near this area. They are crowded near the North Pole and as well as near the South Pole. So we can say that the strength of the magnetic field, we can have its idea by seeing the spacing of the magnetic field lines. Wherever the spacing is less, magnetic field is stronger, and wherever the spacing is more, magnetic field is weaker. So when we look at two different areas around the bar magnet here, by looking at the relative spacing between the magnetic field lines, we can get an idea to compare the magnetic field strength at two different places. Now wherever the lines are crowded, field is stronger. Wherever they are further apart, field is weaker. That's why, see here, as we move away from the bar magnet, I have shown that this distance between the bar magnet and the first line, then first line and the second line, second and third line, the spacing between the field lines, the nearby field lines goes on increasing. So spacing goes on increasing, which means that magnetic field strength becomes weaker as we move away from the magnet. And it is maximum, the strength is strongest near the North Pole and the South Pole. Now one thing more. So let me write here North Pole, South Pole. Now, magnetic field is a vector quantity. So we have now discussed that the spacing, relative spacing between the magnetic field lines give us an idea of the relative magnetic field strength. Wherever the spacing is less, field is stronger. Wherever the spacing is more, field is weaker. Now, since magnetic field is a vector quantity, it has direction also. And remember, for any definition or for the direction, we are going to prefer North Pole as compared to the South Pole. So in this case, we will say the direction in which the North Pole was pointing, North Pole of the compass, magnetic compass needle was pointing, would give us a direction of magnetic field lines. Suppose if I imagine that magnetic compass is placed here, then now this is not a straight line. You know what is tangent. So this is the direction in which the magnetic compass needle would point. It means we can say magnetic field lines give us now the direction in which the magnetic compass needle's north pole would point if magnetic compass is placed there. How will get the direction? Now this is a magnetic field line. So at this point, if I draw a tangent, then I can say that the tangent to the magnetic field lines at any point gives us the direction in which the magnetic compass needle or needle's north pole would point when placed there. Now since this is North Pole, so North Pole would point in this direction. So for every line we are supposed to show an arrow. So now here. Okay, so for each line you are supposed to show an arrow, and you can show one arrow outside the line and one arrow inside the line. So here, north to south and south to north. So for each line you are supposed to show the direction inside the magnet and outside the magnet. Now remember, students, remember that when we have discussed the previous activity, using that activity we can draw these magnetic field lines, but the inside magnetic field lines, the lines inside the bar magnets, cannot be drawn using that activity. Okay, using that activity we can draw these only lines which are lying outside the bar magnet. And we know that that activity is actually, when we do that activity, it is very time consuming and boring. It's a long process, because for one magnetic field line, to draw one magnetic field line, you have to place compass at various positions to get those 2 marks, and hence to draw